Getting started, I'd like to make a couple of announcements and acknowledgments. First of all, the next talk in our series is by Gordon Bauer of Stanford University. His title of his talk is Understanding Narratives, a Case Study in Cognitive Science, and that will be not in this room. It'll be in Stewart Theater on Thursday, October 12th at 4 p.m. Probably most of you have seen the book display that is out there in the North Gallery. There are copies of this program there that you can pick up. And then, again, let me make an announcement that I made last time, and that is the fourth talk in the series by Noam Chomsky has unfortunately, due to health reasons, had to be postponed until fall of 1990. Notice I did not say canceled. It will occur, but not until 1990. Okay, let me also mention that for those of you who wish to continue, there will be time for question and answers after today's lecture, but if you wish to continue talking about the topic of today's lecture with Professor Fodor, he will be available for a kind of informal seminar tomorrow morning at 9:35 until about 11 in Winston 122. Okay, so anyone who wants to join us is welcome. That should be enough about announcements. I also want to remind you, for those of you who were here last Tuesday night, this is all repeat, so bear with me, that the philosophy and religion...
It gives me great pleasure today to welcome Professor Jerry Fodor to the NCSU campus and to introduce him to you. We keep saying that cognitive science is an interdisciplinary field, and Jerry Fodor is the living proof that that's true. His interests are very wide-ranging. No one who is at all interested in any of the component fields of cognitive science can venture far without encountering his work. He has worked not only on traditional topics in the philosophy of mind, philosophy of language, and philosophy of science, but has done work in the foundations of psychology and linguistics. He's furthermore a frequent commentator on work in artificial intelligence. His work is always original, provocative, and important. He's the author of Psychological Explanation, The Psychology of Language with Thomas Bever and Merrill Garrett, The Language of Thought, Representations, a collection of his essays, The Modularity of Mind, and Psychosemantics. Professor Fodor got his PhD in philosophy from Princeton. He's been a fellow at the Center for Advanced Study in Behavioral Sciences, a Guggenheim Fellow, and member of the American Academy of Arts and Sciences. Until 1986, he was professor of philosophy at MIT. He is currently the State of New Jersey Professor of Philosophy at Rutgers and the adjunct professor of philosophy at CUNY Graduate Center. He's currently at work with Zen and Polition on a book entitled Studies in Cognitive Architecture, and that will be his topic today. Professor Fodor.
Thank you both for the introduction and for the invitation to talk here. I have a couple of sort of meta-theoretic comments to make about this paper before I go into it. One is that it comes in two versions. There's the one that I'm proposing to present, and it takes exactly 67 minutes to get through. There's also one there's a shorter form in which the jokes have been deleted. The trouble is, it only takes about 19 seconds to get through, and so it leaves with a lot of nothing to do, considering the length of the trip down and so on. So I am going to give the longer version, but in order to get through it in some finite amount of time, in fact exactly 67 minutes, I want to reserve all the questions and howls of agony and stuff like that to the end. I've had some experience with giving this material before, and what happens invariably is about a third of the way through, some agonized connectionist gets up and starts to gnaw on the chair and stuff like that. And I'm perfectly glad to argue, but let's put it at the end so it'll all be in one place. One more meta-theoretic comment. About 3/4 of what I want to say here has appeared in a cognition article that I wrote with Zen and Polition. Those of you who have read this article may wish to duck out for coffee or a smoke. I'll make some loud noise when I get to the new stuff. The new stuff will be about what the difference is between distributed and localist versions of connectionist models, and why it doesn't matter what the difference is between localist and distributed versions of connectionist models. It's borrowed from an about-to-be-published cognition paper in collaboration with Brian McLaughlin at Rutgers, and I wanted to start out by expressing my indebtedness to both my co-authors for any mistakes or unclarities that may be found in what follows. Okay, there is, I think, exactly one problem about the mind that cognitive science has made some serious progress on. Perhaps I ought to say there is at most one problem about the mind that the cognitive science has made some serious progress on. You can get a feel for the nature of this problem by considering the following passage from Conan Doyle. What we have here is Sherlock Holmes doing his thing at the end of the short story called The Speckled Band. Holmes says, "I instantly reconsidered my position when it became clear to me that whatever danger threatened an occupant of the room couldn't come from either the window or the door. My attention was speedily drawn to the ventilator and to the bell rope which hung down by the bed. The discovery that this was a dummy and that the bed was clamped to the floor instantly gave rise to the suspicion that the rope was there as a bridge for something passing through, and passing through the hole and coming to the bed. The idea of a snake instantly occurred to me, and when I coupled it with my knowledge that the doctor was furnished with a supply of the creatures from India, I felt that I was probably on the right track." At this point, Watson says something to the effect of, "Astonishing, Holmes." The passage purports to be a bit of reconstructive psychology. Holmes offers it as a capsule history of the sequence of mental states which brought him first to suspect and then to believe that the doctor did it with his pet snake. But it bears emphasis that Holmes's story isn't just reconstructive psychology. It does double duty, since it also serves to assemble premises for a plausible inference to the conclusion that the doctor did it with a snake. Because his train of thought is like an argument, Holmes expects Watson to be convinced by the considerations which, when they occurred to Holmes, caused his own conviction. What connects the causal history aspect of Holmes's story with its plausible inference aspect is the fact that the thoughts that cause the belief that so-and-so, the belief that P, provide often enough reasonable grounds for believing that P. Were this not the case, were there not this general harmony between the semantical and the causal properties of thoughts, so that, as Holmes puts it in another story, one true inference invariably suggests others, were there not this parallelism, there wouldn't, after all, be much profit in thinking. So here's a fact. Trains of thought are often like arguments. In particular, they often lead from entertaining true premises to entertaining true conclusions. This fact engenders a problem. The problem is, suppose that the mind is a mechanism, and after all, what else could it be, since its states have causal powers? Supposing it is a mechanism, it would be nice to know how a mechanism, a piece of physical matter, could have this property that minds have. How the state transitions of a mechanism could be like arguments in the way that the state transitions of minds are like arguments. This is the problem that cognitive science has made some progress on. In my view, it's in fact the problem that defines the field. It's very often hard to see the problems that cognitive scientists work on, hard even for the cognitive scientists to see the problems that they work on as really being instances of this problem. How could the state transitions of a mind have the property that they lead one from true beliefs to true beliefs in some argument-like way? But I think you don't have to scratch very much to reveal the problem as having that complexion in any area of the field. So, for example, one thing that cognitive scientists work on is perception. Being interested in perception, at least from this computational point of view, is being interested in the question how information about, let's say, light waves or auditory energy or whatever at the periphery of an organism could lead by some series of computational steps to the formation of true beliefs about the distal layouts of the organism's environments. So you can, and indeed psychologists in Helmholtz have, thought of perception as basically an inference-like phenomenon where the premises of the inference are statements about proximal states of the organism, proximal sensory states of the organism, what's happening at the retina, in effect, and the conclusions of the inference are perceptual beliefs like, oh, there must be a chair out there. What I believe is that if you go through the exercise of looking at the kinds of problems that cognitive scientists work on in any field, they always have this structure. They're always about how the state transitions of some cognitive mechanism could be argument-like in that they lead one from informational truths to informational truths when things go properly. The British logician Turing suggested what I strongly suspect is the right solution to this problem about how sequences of thought could be like arguments. And what cognitive science has been doing ever since Turing is, in effect, taking in his laundry. It's been investigating the implications of his suggestion for various fields of cognitive processing. Turing's idea was that you can explain the analogy between trains of thought and argument, consonant with assuming that the mind is a mechanism, if you also assume the following two things. First, that mental states are syntactically structured, and second, that the syntactic structure of a mental state determines its causal role in mental processes. I'll sometimes refer to this as the language of thought picture of the mind because the most obvious example of things that have syntactic structure is sentences. In fact, it wouldn't be very misleading to say that Turing's idea was that thinking is a syntactic operation on mental sentences. And what Turing argued, I think persuasively enough so that one wants to follow out the research program that he set forward, what Turing argued was that if you assume that thinking is a syntactic operation on mental sentences, then the nature of the analogy between trains of thought and arguments, the truth-preserving character of trains of thought, can be made compatible with a mechanistic theory of the mind. I don't know how to reconstruct in Turing's kinds of terms the argument that I just quoted from Sherlock Holmes. We're a long way from being able to do that. But I can do a sort of microcosm of the Holmes argument. In fact, the simplest case I could think of to show you how Turing's proposal works. So consider the following example. Having the thought that Mary went to the store and Sam went to the store often causes one to infer that Mary went to the store, which is to say that causal trains of thoughts often parallel arguments from P and Q to P. So here's a sort of kindergarten level question about how causal chains of thought, how causal chains of mental states could be like arguments. How can one model for a mechanism arguments that take one from the premise P and Q, say John went to the store and Mary went to the store, to the conclusion P, say John went to the store? What kind of mechanism would have this property? Well, Turing invites one to consider a certain kind of device, since come to be known as a Turing machine, for obvious reasons, which is structured in the following kind of way. The device consists of two parts. Let me see if I can set this up so it's visible to at least 30% of the audience. Okay. The device consists of two parts. One part I'll call a reader or a head, and we'll come to that in just a moment, and the other part called a tape. The tape is thought of conventionally as a tape, something you could buy from Triple M, Ministry of Mining Manufacturing, except that unlike the tapes that they sell, this one is thought of as infinite in both directions. Okay, so you've got quite a lot of this stuff. The tape is divided into squares, though in fact this part doesn't matter. For convenience, the tape is divided into squares, and one can think of what you can do in these squares is write symbols on them. Right. So, for example, we're going to be able to write on the symbols that constitute our argument, like P, Q, P, N, Q, R, anything we like. Okay. We've got some alphabet, some vocabulary, and one can use the symbols in this vocabulary to write on the tape. And we'll assume that, again, for purposes of convenience, and again, it doesn't matter, we'll assume that the tape is conventionally divided into areas in which we're going to write the premises of our arguments and areas in which we're going to write the conclusions of our arguments. Okay, so how does it work? Well, you start the thing going by writing on the tape the premise of the argument, namely P and Q, and this part of the device has certain mechanical capacities. It can identify items in the vocabulary that you're writing on the tape. It can move the tape. It can delete items from the tape, and it can write items on the tape. In fact, that's all it can do. Okay. And that's all mechanical. I mean, one can actually imagine bits of machinery which will do any of those things. Here's how the machine works in the case of this particular little baby argument from P and Q to P. You set the thing running, the machine scans the portion of the tape on which the premise is written, that is, it just reads these items, and its mechanical structure has the following property. It's so set up that when it reads P and Q in the premise part of the tape, it jumps and plugs and moves the tape until it gets over to the part of the tape on which you decided to write your conclusions, and what it does is it copies this symbol in this part of the tape. That business of scanning the premise of the argument, moving the tape, and writing one of the symbols, writing a constrained symbol, a certain symbol, down in the conclusion part, that's the way this mechanism models the business of inferring from premises to conclusions, and in particular, the operation of copying the P from P and Q in the premise part of the tape onto the conclusion part of the tape is what counts for this mechanism as an instance of inferring from P and Q to P. So that's the way the device works. And since mechanisms of this kind are actually constructible, I mean, that's basically the kinds of things that classical computers are, standard computers are. Since mechanisms of this kind are actually constructible, one can answer, at least for this baby device, at least for this baby inference, the inference from P and Q to P, you can answer the question, how can a purely mechanical device be such that its state transitions are modelable by this inference, or instances of this inference. Okay. Notice that according to, and this is a point I want to emphasize because it's going to be the key issue about connectionist models. Notice that according to this kind of story, in which, notice that according to this kind of story, the things that count as analogs to mental processes are actually manipulations of linguistic objects. They're manipulations of things like inscriptions of P and Q written on the tape of the machine. Moreover, these are linguistic objects for which logical, syntactic, and semantic structure, by which syntactic and semantic structure in particular is exhibited. It's not an accident of the way this machine works that the very object which appears on the conclusion part of its state when it infers from P and Q to P appears as a constituent, a syntactic part of the premise, of its representation of the premise of the argument. In fact, that's how the machine works. The machine is, in effect, doing a syntactic analysis of the premise, finding P as one of the constituents, and simply copying that constituent on the conclusion part of the tape. It's extremely sensitive to the machine to the actual syntactic configurations of the objects on which it operates, to the way they're put together from parts. The best way to see how sensitive it is to notice the following fact about this machine. If you were to replace the premise P and Q with something semantically equivalent, like, for example, not P and Q, and then tell the machine to go ahead and do its thing. So you replace the premise with something that's semantically equivalent but syntactically distinct, and turn the button on that starts the machine going. What happens to the machine is that it stops, it grinds to a halt. You have to tell it what to do about the various syntactical structures that it encounters, even when these structures are semantically equivalent to things that it already knows about. So this device is super sensitive. First of all, this is a device that operates on objects that have internal syntactic structure. They're made out of parts. P appears as part of the thing that means P and Q. The symbol that expresses the proposition John went to the store is part of the symbol that expresses the proposition John went to the store and Mary went to the store. The thing has syntactic internal structure. And the operations of the machine are very sensitive to that syntactic internal structure. Right? In fact, they compute on strings. The operations which they'll perform on a string is entirely determined by the syntactic organization of the string plus the mechanical structure of the machine. So that's why this is a language of thought kind of device. Its operations are operations on syntactically and semantically structured objects. Okay, so that's how this thing works for one case, and now all we have to do is get it to work for the trillion other cases in which mental processes are like arguments and cognitive science comes to an end. That's the program, that's the project, to treat the relation between steps in any mental process and the end of that process on the model of the relation between the way this, on the model of the way that this machine treats the relation between the premise of the argument P and Q and the conclusion of that argument P. Okay, so let me summarize the Turing or language of thought or classical picture of the machine. Mental states involve causal interactions among semantically evaluable states. That is, for example, they're set up to preserve semantical properties like truth. These interactions typically take one from true premises to true conclusions, and what we want is a mechanism whose interactions, whose state transitions will preserve that property. You can get such a mechanism, or so we hope, if you assume that mental states are syntactically structured and that mental processes are syntactical operations on mental states. That's the Turing program. That's the problem it seeks to provide an answer to. And the rest is just actually doing the research. As far as the general structure of cognitive science is concerned, this lecture might just as well stop here, since I've told you what problem cognitive science is about, and I've told you the one good idea that anybody's had for solving this problem. Everything else worth knowing about in cognitive science is just elaboration in aid of what Fodor calls lending verisimilitude to an otherwise bald and unconvincing tale. However, I promised to say something about connectionism, and so here goes. Let me suggest an alternative model of how you might infer P from P and Q, an alternative to this language of thought model. You might have an electrical network. This also will be a mechanism just like this one. An electrical network set up in the following way. It doesn't really matter that it be electricity, by the way. I mean, it could be hydraulic or wind or anything you like. I mean, it doesn't make any difference to the general picture. The network's set up in the following kind of way. It consists of three contacts. In fact, it'll be graphic if we treat these contacts as sockets into which you can screw light bulbs. At each contact, there's a light bulb, and again, for purposes of making it graphic, we'll write formulas on the light bulb. So they'll display the formula, the light bulb will display the formula when it lights up. Okay. So on this one, we'll put P and Q. That's the premise of our argument. On this one, we'll put P, and on this one, we'll put Q. And now, how does this thing work? Well, this network, this circuit, is so set up as to have the following property. You can apply voltages here, and the connectivity of the network is such that when you apply a voltage here sufficient to make this bulb light up, when you supply an electric current to here sufficient to make this bulb light up, this current is diffused through the network, and this bulb lights up too. So does this one, but for our purposes it doesn't matter. Okay. So what corresponds in this kind of system to inferring from P and Q, to the process of inferring from P and Q, is the process whereby lighting up this light bulb, which corresponds to accepting the premise P and Q, lights up this light bulb, which corresponds to accepting the conclusion P. I don't think I said that right, so I'll say it again. What corresponds to inferring from P and Q to P is the process whereby a current applied at this light bulb, which causes the P and Q premise to light up, also causes the P premise to light up. Okay? Now, this machine looks, in some respects, as though it was a language of thought machine too. The first thing to understand about connectionism is why it's not. Notice that the very same formulas that you write on the tape of a classical machine, over which the operations of the machine are defined, these very same formulas appear on the light bulbs in this machine. Okay? However, there is the following difference between the two machines. if you erase the formulas from the tape, remember we had a reader and formulas written on here in the computational code and so on. And the presence of a formula on a tape triggered the operation that corresponded to drawing an inference in this machine. In this machine, if you erase the formulas from the tape, or if you replace them by, as I suggested before, semantically equivalent but syntactically distinct formulas, that's equivalent to putting sand in the gears, right? The machine comes to a halt. On this machine, if you erase the formulas from the light bulb, what happens? Answer, nothing, right? If you erase the formulas from the light bulb, it will still be the case that applying a charge here, sufficient to make this light bulb go on, eventuates in this light bulb going on, okay? In this language, mechanism,